Okay, today we're going to do Newton's first. Okay, not to mention all these other terms we're going to have. That is actually Newton's second law. And after this we'll do momentum. So, there's a Newton's cradle. Cool little contraption. Used to have one, but I don't anymore. I should get another one. Okay, Newton's first law. There's not really much we can do as far as formulas here. It's just a concept. And in our book we have an example of you in a car. So if you're sitting in the passenger seat and you're traveling down the road and the driver cranks on the wheel left and the car goes in this direction, what would happen? What happens to you? And most people say you hit the door. But actually what is happening is the door is actually hitting you. You want to travel in the same direction that you were traveling. It's the car that's moving underneath you and hitting your arm. So it's a little bit opposite to what we've previously believed. Another example, what if you're sitting at a stoplight and you're stopped? And you get, unfortunately, rear-ended. And it seems like you're moving backwards. That's what people tend to think. And one of the unfortunate results of this accident is people getting whiplash. It's quite common. I'll actually show you a video in a sec how you can minimize the amount of whiplash that you get, which is always nice. But you don't actually move backwards. What happens is you are sitting still and it's the car that is moving underneath you. The seat carries you through, and the reason you get whiplash is there's nothing there to support your head. We do have headrests, and that's the video I'm going to show you in a sec. What's actually happening, like I said, is you're not moving backwards, it's the car that's moving forwards. So it's a little bit opposite to what we think. Inertia. Here is the definition. Okay, every object in the universe has mass, has inertia. I got a little video first to show you about Newton's law. So let's just watch this. It's the old pull the tablecloth out without wrecking the dishes. Let's see how these kids do. Well, they didn't do too well.
The law of inertia bikes will stay still unless you push or pull on them. There are two safety devices in your car to protect you from the effects of inertia. The first is your seatbelt. When the front end of your car rams another object, your car will suddenly stop or slow down. Because of inertia, your body will want to stay moving at whatever speed it was moving before the accident. If you're not wearing a seatbelt, this means you will hit a windshield. The seatbelt provides a force to stop your body's forward motion.
I don't know, the music's so loud.
A headrest. When your car is hit from behind, the car is suddenly pushed forward. Your head will want to stay still, but your body will be pushed forward by the seat. This causes your head to feel like it is snapping back. Your head is actually staying still because of inertia, while the rest of your body is being pushed. Your headrest pushes your head forward with your body so that you don't suffer from whiplash. Look at the difference between a headrest that is properly set versus one that is set too low to push your still head forward.
Okay, so lots of us know about seat belts, and we're told over and over that they save lives and we should be wearing them, but not many people actually adjust your headrest, which is what you should do. So, what is Newton's first law in words? We've talked about it a bit. This is it. Where's my stuff? There we go. Okay. This is one way to word it. A body will continue to move at the same speed and in the same direction for as long as there is no unbalanced force acting on it. We did some problems previously where we had a crate moving along the ground where the applied force was the same as the friction force. If these things are equal, it can move at some speed v, but it's not accelerating and it's not decelerating. It's just moving at a constant speed. Same speed, same direction. Once we have an unbalanced force, this is Newton's second law, which we'll talk about in a sec, then it will start to accelerate. But as far as the first law is concerned, it will move at the same speed in the same direction as long as there is no force. Another wording is things in motion stay in motion, and things at rest stay at rest, unless there is an unbalanced, let's call it, or a net force. Okay, that's another wording. Some other wording, put another way, an object wants to keep doing what it's already doing. If it's in motion, it wants to stay in motion. If it's at rest, it wants to stay at rest, unless another force is acting on it. Okay, that's Newton's first law. Newton's second law. This is one where we can actually do some problems, do some equations, figure some stuff out. Okay, and let's just start right here. There it is. That's Newton's second law. It's a formula. Let's actually, well, we've talked about this before when we were talking about force of friction formula. We can say the force of friction is directly proportional to the normal force. The more weight something has, actually let's go this direction, the more weight something has, the greater the weight, the larger the force is needed to actually push this thing. Force of friction is also directly proportional to mu. The higher the friction force needed to push this thing. We've seen some other formulas. Fg is mg. The larger the mass, the more the weight, the more the force of gravity. This can be written a different way. F is ma, and that is how it looks on the back of our book in our formula sheet. Okay, but if it's in this form, let's see what this says. The rate at which it accelerates depends directly on the unbalanced force. Okay, acceleration is directly proportional to the force. The larger the force, the faster this thing's going to accelerate. Also, the acceleration, the rate at which it accelerates, is inversely proportional to the mass. Because mass here is on the bottom of this equation, okay, the larger the denominator, then the smaller this will be. Okay, mathematically, I hope we realize that happens. Okay, it's inversely proportional. Okay, that is what it's on our back of our book. This isn't just any old force though. What we want to put here is F net. It is the net force, the unbalanced force. Okay, it's important. It's not just force of friction. It's not just force of gravity. It is the difference of two forces on a body. It's the unbalanced force. Okay, so I'm going to get you guys to do those ones. I will do a couple of others. So, like I said previously, we did not have a net force. We gave you questions where there's an applied force. Let's say it's 100 newtons. There's a friction force because this thing's sliding on the table. And let's say if it was 100 newtons, I would need to push this at something greater than that in order to get this thing to move. But we can have constant velocity if our applied force equals our friction force. It can be sliding in that direction with some velocity. Once we have an unbalanced force, we have multiple forces on this perhaps, okay, then we'll have an acceleration. So now, if I push or pull this thing with 120 newtons, I have a 20 newton difference there. Okay, that is my unbalanced force. That's my net force. If I take the difference of this, 20 newtons will cause this thing not to have a constant speed. We're going to have a changing speed. We're going to have an acceleration there. Okay, so these are the numbers. Difference, you can look at it, but as a formula, you would say the applied force minus the friction force is the net force. This is the one that is in Newton's second law. That's the one we can determine the acceleration with if we know the mass of this thing. Okay, I kind of missed something here though. Don't forget, if this is our free body diagram, we want to put Fg there, and because it's not going up or down, there must be some force here balancing Fg, and that's the normal force. Anytime we have a normal force here, if it's sitting on this table perpendicularly, we can say the normal force is the force of gravity, because those two forces are balanced. Okay? So, a couple of examples. Let's just do this one in the book. A 45 Newton block. Stop right there. What does that mean? That's the weight of this block. It's 45 newtons. Okay? This arrow should be the first thing we do when we do our free body diagram. Force of gravity. Our formula for Fg is mg. If I know the mass, and I know this thing's on Earth, g is 9.8, I can figure this out, but in this case, they're already giving me the force. Right? That's 45 newtons. That is a force. So now, with this, I could figure out the mass. If I divide this by 9.8, then my mass is going to be... Close the door. 4.6 kilograms. All right, but they're telling me this in the question anyway. Okay, normal force. It's equal to the force of gravity, okay, because this thing isn't going up or down. It's not accelerating up or down, it's going sideways. So, let's keep reading. The coefficient of friction, that's mu, is 0.333, no units for mu. A force of 25 newtons is applied. Okay, they have their applied force going left. Fa is 25 newtons. At what rate will the block accelerate? I want to know the acceleration. All right, opposing my applied force is my force of friction. And I know this thing's accelerating, so there must be a net force. Here's my formula. Okay, if there's some positive acceleration, I know this thing has mass, so there must be a net force. The net force is the unbalanced force. It's the difference between the applied force and the friction force. I know the applied force is 25 newtons. I'm trying to find the acceleration. So F net is ma. So let's substitute that in here. That's what I'm trying to find. I need to know the force of friction then. I have to have only one variable in a formula. I can't have two. I won't be able to solve it. That's where this formula comes in. Okay, force of friction is, I have mu, Fn is equal to Fg, and I know that's 45 newtons. So my force of friction is 14.99, let's call that 15 newtons. Okay, so MA, what's M? I know it's 4.6. 25 minus 15 is 10. Divide by 4.6. So my acceleration is 2.2, let's round that, meters a second squared is units for acceleration. Okay, it's accelerating. I have a net force, not constant velocity. The speed is changing at a rate of 2.2 meters per second per second. Let's do one more because we need something now going up or down. So we got some space here in the book. Let's write this. Example. What is the air resistance? What's another way to say air resistance? Force of friction, yes. For a 4 kilogram bowling ball falling, there is an English word. What do you think when you hear the word falling? Is it going sideways? Nope. It's going vertically, not horizontally, in a direction down towards Earth. Falling with acceleration of 8 meters a second squared. So, what is G? G is 9.8. That means in a vacuum, this thing will accelerate, anything will accelerate towards Earth at 9.8 meters a second squared. Because that says 8. I know this thing's going slower than this. There is something holding it back. Friction, otherwise called air resistance. Okay? So, what is the air resistance? That's what I'm trying to find. We should start with, this one's easy to draw because it's round, it's a circle, a sphere, it's a bowling ball. First thing, it's going down. I have a force of friction, that's what I'm trying to find out. Fg is mg, and this is on Earth. Okay, so like I said, if there was no force of friction, this thing would fall at 9.8. But there is. Any other forces on this bowling ball? Anything going sideways? No. That's it. There's my sphere. Okay, what do I know? I know the force of friction is mu Fn. I know... No, there is no Fn, is there? There's no normal force. And I don't know mu, so that's probably not that helpful. I know the net force is mass times acceleration. I have mass. I have an acceleration. So why don't we get that? My net force is 32 newtons. But remember, the net force is also the unbalanced force. It's the difference between that and this. That's what's causing the acceleration. If these were equal, it would move at a constant speed, but it would not accelerate. When something's falling, we have a word for that. It's called terminal velocity. But there is an unbalanced force. What's 4 times 9.8? 39.2. Well, actually, let's write it out like this first. My net force is the unbalanced force, the difference of those two, okay? That's not a formula on the back of your book. That's just something you're going to have to remember. That's the concept. So now let's put in numbers. Fg, I just did that, 39.2 newtons minus a force of friction. That's what I'm trying to find out. But wait a minute, don't I know F net? Yeah, that's mass times acceleration. That's 32. So 32 is 39.2 minus FF. Let's rearrange this. Let's throw that on that side of the equation and change the sign. Okay, let's throw this on that side of the equation and change its sign from positive to negative. And if you take the difference there, it looks like we get 7.2. That's a force. It's newtons. And that's your force of friction. Okay? So, that's one way to do it. You want to see how a kid in big school would do it? When I say big kids school, I mean university, maybe even grade 12. Here's kind of what you should do, is generate a formula specific to this question. I know F net is ma, that's Newton's second law. I know the difference of these two forces is the net force. So let's combine these. Okay. So Fg, I know is mg. Force of friction is what I'm trying to find. And if I rearrange this formula, again I put force of friction over on the right, change the sign, put this on the left, change the sign. You remember factoring? Why did we teach this stuff in grade 10 and 11? So maybe you could do something like that. Okay? So that's about as simplified as I can get this thing. This is obviously not on the back of your book. In this case, it's a formula that will work. Now put in your numbers. What's the mass? 4. G is 9.8. I know the acceleration of this thing was 8. Tells me that in the question. Okay, put that in here. So what is 4 times 1.8? We get the same thing. 7.2 newtons. Okay, it's just, instead of putting the numbers in first, we rearrange our formula, make it as sweet as possible, then we put the numbers in. Sometimes that can be a lot easier. And if I was solving for the mass here, right, then maybe that's the way I'd like to do it, because then I isolate m for itself in this formula. Okay, so that's the big kid way. Questions? So you do page 108, 2 to 4, page 110, 1 to 3, and page 112, 1 to 4. Okay.